Abrasive blasting is the operation of forcibly propelling a stream of abrasive material against a surface under high pressure to smooth a rough surface, roughen a smooth surface, shape a surface, or remove surface contaminants. A pressurized fluid, typically compressed air, or a centrifugal wheel is used to propel the blasting material. The first abrasive blasting process was patented by Benjamin Chew Tilghman on the 18th of October 1870. There are several variants of the process, using various media. Some are highly abrasive, whereas others are milder. The most abrasive are shot blasting and sand blasting. Moderately abrasive variants include glass bead blasting and media blasting with ground-up plastic stock, walnut shells and corn cobs. A mild version is soda blasting. In addition, there are alternatives that are barely abrasive and non-abrasive, such as ice blasting and dry ice blasting. Types: wet abrasive blasting. One of the original pioneers of the wet abrasive process was Norman Ashworth, who found the advantages of using a wet process a strong alternative to sand blasting, which is banned in many countries. Common features include the ability to use extremely fine coarse media with densities ranging from plastic to steel, the ability to use hot water and soap to allow simultaneous degreasing and blasting, elimination of dust, so silicaceous materials can be used without worry, hazardous material or waste can be removed without danger, e.g., removal of asbestos, radioactive, or other poisonous products from components and structures leading to effective decontamination. The process is available in all conventional formats including hand cabinets, walk-in booths, automated production machinery and total loss portable blasting units. Process speeds can be as fast as conventional dry sand blasting when using the equivalent size and type of media. However, the presence of water between the media and the substrate being processed creates a lubricating cushion that can protect both the media and the surface from excess damage. This has the dual advantage of lowering media breakdown rates and preventing impregnation of foreign materials into the surface. Hence, surfaces after wet blasting are extremely clean. There is no embedded secondary contamination from the media or from previous blasting processes, and there is no static cling of dust to the blasted surface. Subsequent coating or bonding operations are always better after wet blasting than dry blasting because of the cleanliness levels achieved. The lack of surface recontamination also allows the use of single equipment for multiple blasting operations, e.g., stainless steel and carbon steel items can be processed in the same equipment with the same media without problems. Bead blasting. Bead blasting is the process of removing surface deposits by applying fine glass beads at a high pressure without damaging the surface. It is used to clean calcium deposits from pool tiles or any other surfaces, remove embedded fungus, and brighten grout color. It is also used in auto body work to remove paint. In removing paint for auto body work, bead blasting is preferred over sand blasting, as sand blasting tends to invite rust formation under repainted surfaces. It's additionally used in cleaning mineral specimens, most of which have a Mohs hardness of 7 or less and would thus be damaged by sand. Wheel blasting. In wheel blasting, a spinning wheel propels the abrasive against an object. It is typically categorized as an airless blasting operation because there is no propellant used. A wheel machine is a high-power, high-efficiency blasting operation with recyclable abrasive. Specialized wheel blast machines propel plastic abrasive in a cryogenic chamber, and is usually used for deflashing plastic and rubber components. The size of the wheel blast machine, and the number and power of the wheels vary considerably depending on the parts to be blasted. blasted as well as on the expected result and efficiency. The first blast wheel was patented by Wheelabrator in 1932. Hydroblasting, commonly known as water blasting, is commonly used because it usually requires only one operator. In hydroblasting, a highly pressured stream of water is used to remove old paint, chemicals, or build-up without damaging the original surface. This method is ideal for cleaning internal and external surfaces because the operator is generally able to send the stream of water into places that are difficult to reach using other methods. Another benefit of hydroblasting is the ability to recapture and reuse the water, reducing waste and mitigating environmental impact. Microabrasive blasting. Microabrasive blasting is dry abrasive blasting process that uses small nozzles to deliver a fine stream of abrasive accurately to a small part or a small area on a larger part. Generally, the area to be blasted is from about 1 square millimeter to only a few cm2 at most, also known as pencil blasting. The fine jet of abrasive is accurate enough to write directly on glass and delicate enough to cut a pattern in an eggshell. The abrasive media particle sizes range from 10 micrometers up to about 150 micrometers. Higher pressures are often required. The most common microabrasive blasting systems are commercial bench-mounted units consisting of a power supply and mixer, exhaust hood, nozzle, and gas supply. The nozzle can be handheld or fixture-mounted for automatic operation. Either the nozzle or part can be moved in automatic operation. Automated blasting. Automated blasting is simply the automation of the abrasive blasting process. Automated blasting is frequently just a step in a larger automated procedure, usually involving other surface treatments such as preparation and coating applications. Care is often needed to isolate the blasting chamber from mechanical components that may be subject to dust fouling. Dry ice blasting. In this type of blasting, air and dry ice are used. Surface contaminants are dislodged by the force of frozen carbon dioxide particles hitting at high velocity, and by slight shrinkage due to freezing, which disrupts adhesion bonds. The dry ice sublimates, leaving no residue to clean up other than the removed material. Dry ice is a relatively soft material, so is less destructive to the underlying material than sand blasting. Bristle blasting. Bristle blasting, unlike other blasting methods, does not require a separate blast media. The surface is treated by a brush-like rotary tool made of dynamically tuned high-carbon steel wire bristles. Repeated contact with the sharp, rotating bristle tips results in localized impact, rebound, and crater formation, which simultaneously cleans and coarsens the surface. Equipment. Portable blast equipment. Mobile dry abrasive blast systems are typically powered by a diesel air compressor. The air compressor provides a large volume of high-pressure air to a single or multiple blast pots. Blast pots are pressurized, tank-like containers filled with abrasive material, used to allow an adjustable amount of blasting grit into the main blasting line. The number of blast pots is dictated by the volume of air the compressor can provide. Fully equipped blast systems are often found mounted on semi-tractor trailers, offering high mobility and easy transport from side to side. Others are hopper-fed types, making them lightweight and more mobile. In wet blasting, the abrasive is introduced into a pressurized stream of water or other liquid, creating a slurry. Wet blasting is often used in applications where the minimal dust generation is desired. Portable applications may or may not recycle the abrasive. Blast cabinet. A blast cabinet is essentially a closed-loop system that allows the operator to blast the part and recycle the abrasive. It usually consists of 4 components: the containment, the abrasive blasting system, the abrasive recycling system, and the dust collection. The operator blasts the parts from the outside of the cabinet by placing his arms in gloves attached to glove holes on the cabinet, viewing the part through a view window, turning the blast on and off using a foot pedal or treadle. Automated blast cabinets are also used to process large quantities of the same component and may incorporate multiple blast nozzles and a part conveyance system. There are 3 systems typically used in a blast cabinet. 2. Siphon and pressure. A dry and 1 is wet. A siphon blast system uses the compressed air to create vacuum in a chamber. The negative pressure pulls abrasive into the blast gun, where the compressed air directs the abrasive through a blast nozzle. The abrasive mixture travels through a nozzle that directs the particles toward the surface workpiece. Nozzles come in a variety of shapes, sizes, and materials. Tungsten carbide is the liner material most often used for mineral abrasives. Silicon carbide and boron carbide nozzles are more wear-resistant and are often used with harder abrasives such as aluminum oxide. Inexpensive abrasive blasting systems and smaller cabinets use ceramic nozzles. In a pressure blast system, the abrasive is stored in the pressure vessel, then sealed. The vessel is pressurized to the same pressure as the blast hose attached to the bottom of the pressure vessel. The abrasive is metered into the blast hose and conveyed by the compressed gas through the blast nozzle. Wet blast cabinets use a system that injects the abrasive liquid slurry into a compressed gas stream. Wet blasting is typically used when the heat produced by friction in dry blasting would damage the part. Blast room. A blast room is a larger version of a blast cabinet, and the blast operator works inside the room. A blast room includes 3 of the 4 components of a blast cabinet: the containment structure, the abrasive blasting system, and the dust collector. Most blast rooms have recycling systems ranging from manual sweeping and shoveling the abrasive back into the blast pot to full reclaim floors that convey the abrasive pneumatically or mechanically to a device that cleans the abrasive prior to recycling. Media. In the early 1900s, it was assumed that sharp-edged grains provided the best performance, but this was later demonstrated not to be correct. Mineral. Silica sand can be used as a type of mineral abrasive. It tends to break up quickly, creating large quantities of dust, exposing the operator to the potential development of silicosis, a debilitating lung disease. To counter this hazard, silica sand for blasting is often coated with resins to control the dust. Using silica as an abrasive is not allowed in Germany, United Kingdom, Sweden, or Belgium for this reason. Silica is a common abrasive in countries where it is not banned. Another common mineral abrasive is garnet. Garnet is more expensive than silica sand, but if used correctly, will offer equivalent production rates while producing less dust and no safety hazards from ingesting the dust. Magnesium sulfate, or chiaceride, is often used as an alternative to baking soda. Agricultural, typically crushed nutshells or fruit kernels. These soft abrasives are used to avoid damaging the underlying material, such when cleaning brick or stone, removing graffiti, or the removal of coatings from printed circuit boards being repaired. Synthetic. This category includes cornstarch, wheat starch, soda sodium bicarbonate, and dry ice. These soft abrasives are also used to avoid damaging the underlying material, such when cleaning brickstone, removing graffiti, or the removal of coatings from printed circuit boards being repaired. Soda blasting uses baking soda, which is extremely friable. The microfragmentation on impact, exploding away surface materials without damage to the substrate. Additional synthetic abrasives include process byproducts, engineered abrasives, and recycled products. Metallic, steel shot, steel grit, stainless steel shot, cut wire, copper shot, aluminum shot, zinc shot. Many coarser media used in sandblasting often result in energy being given off as sparks so light on impact. The colors and size of the spark glow varies significantly, with heavy bright orange sparks from steel shot blasting, to a faint blue glow from garnet abrasive. Safety. Cleaning operations using abrasive blasting can present risks for workers' health and safety, specifically in portable air blasting of blast-room applications. There is a large amount of dust created through abrasive blasting from the substrate and abrasive. Although many abrasives used in blasting rooms are not hazardous in themselves, other abrasives have varying degrees of hazard. However, in all cases the use can present serious danger to operators, such as burns due to projections, falls due to walking on round shot scattered on the ground, exposure to hazardous dusts, heat exhaustion, creation of an explosive atmosphere, and exposure to excessive noise. Blasting rooms and portable blasters equipment have been adapted to these dangers. Blasting lead-based paint can fill the air with lead particles, which can be harmful to the nervous system. In the U.S., the Occupational Safety and Health Administration mandates engineered solutions to potential hazards. However, silica sand continues to be allowed, even though most commonly used blast helmets are not sufficiently effective at protecting the blast operator if ambient levels of dust exceed allowable limits. Adequate levels of respiratory protection for blast operations in the United States is approved by the National Institute for Occupational Safety and Health. Typical safety equipment for operators includes positive pressure blast hood helmet. The hood helmet includes a head suspension system to allow the device to move with the operator's head, a view window with replaceable lens, a lens protection, and an air feed hose. Grade D air supply. The air feed hose is typically attached to a Grade D pressurized air supply. Grade D air is mandated by OSHA to protect the worker from hazardous gases. It includes a pressure regulator, air filtration, and a carbon monoxide monitor alarm. An alternative method is a self-contained, oil-less air pump to feed pressurized air to the blast hood helmet. An oil-less air pump does not require an air filter, a carbon monoxide monitor alarm, because the pressurized air is coming from a source that cannot generate carbon monoxide. Hearing protection, earmuffs or earplugs. Body protection. Body protection varies by application but usually consists of gloves and overalls or a leather coat and chaps. Professionals would wear a cordura canvas blast suit. In the past, when sandblasting was performed as an open-air job, the worker was exposed to risk of injury from the flying material and lung damage from inhaling the dust. The silica dust produced in the sandblasting process would cause silicosis after sustained inhalation of the dust. In 1918, the first sandblasting enclosure was built, which protected the worker with a viewing screen revolved around the workpiece, and used an exhaust fan to draw dust away from the worker's face. Silicosis is still a risk when the operator is not completely isolated from the sandblasting apparatus. Sandblasting also may present secondary risks, such as falls from scaffolding or confinement in a small space. Carbon monoxide poisoning is another potential risk from the use of small gasoline-powered engines in abrasive Sandblasting. Several countries and territories now regulate sandblasting such that it may only be performed in a controlled environment using ventilation, protective clothing and breathing air supply. Worn look jeans. Many consumers are willing to pay extra for jeans that have the appearance of being used. To give the fabrics the right worn look, sandblasting is used. Sandblasting has the risk of causing silicosis to the workers, and in Turkey, more than 5,000 workers in the textile industry suffer from silicosis, and 46 people are known to have died from it. Silicosis was shown very common among former denim sandblaster in Turkey in 2007. A 2015 study confirmed that silicosis is almost inevitable among former sandblasters. Sweden's Fair Trade Center conducted a survey among 17 textile companies that showed very few were aware of the dangers caused by manually sandblasting jeans. Several companies said they would abolish this technique from their own production. In 2013, research claimed that in China some factories producing worn-look jeans are involved in varied non-compliance with health and safety regulations. Applications. The lettering and engraving on most modern cemetery monuments and markers is created by abrasive blasting. Sandblasting can also be used to produce three-dimensional signage. This type of signage is considered to be a higher-end product as compared to flat signs. These signs often incorporate gold leaf overlay and sometimes crushed glass backgrounds, which is called smolts. When sandblasting wood signage, it allows the wood grains to show and the growth strings to be raised, and is a popular way to give a sign a traditional carved look. Sandblasting can also be done on clear acrylic glass and glazing as part of a storefront or interior design. Sandblasting can be used to refurbish buildings or create works of art. Modern masks and resists facilitate this process, producing accurate results. Sandblasting techniques are used for cleaning boat hulls, as well as brick, stone, and concrete work. Sandblasting is used for cleaning industrial as well as commercial structures, but is rarely used for non-metallic workpieces. Bibliography. Manufacturing Processes Reference Guide by Robert H. Todd, Del K. Allen, and Leo Elting. First ed. Tool and Manufacturing Engineer's Handbook. Volume 1. Machining, 4th edition, 1983. Society of Manufacturing Engineers.